So we're going to continue looking at congruences today. I'll begin with the short review. I'll begin with a short review of what we covered last time, and give you a chance to ask any questions or queries that you might have from the last lecture. Okay. Okay, so last time we started to look at the congruence relation, this idea of considering the integers modulo some number. You've seen an example of that with some of the work we're doing in cryptography, where you've been encoding the alphabet with the integers 0 through 25 or 1 through 26. So whatever choice you're using, and by performing, you can base various cryptographic schemes using the operations of addition and multiplication modulo 26. It gives a nice kind of compact way of dealing with that encoding of the alphabet. So we also saw an example where we were able to prove a very nice number theory result. I reviewed this last time. This result where p being a prime number implies that p squared plus 2 is not a prime. Which on the face of it looks perhaps quite a challenging thing to try and prove. There's an infinite number of prime numbers, an infinite number of cases to check, but we don't have a good description of all the prime numbers. We don't have any good, direct, explicit description of all the prime numbers that you might use to examine p squared plus 2. But we found that the trick here was to think of, essentially to think of p, what p was congruent to modulo 6. In other words, look at the remainders that you get when you divide p by 6. And we pretty soon agreed that you could only have the options 1 and 5. Sorry, this is for all prime numbers greater than or equal to 5. The other options, 2, 3, 4, are excluded. 0, because those would lead to p being a composite number. So prime number, we recognize, could only be congruent to two things modulo 6. And when you check both of these, so when you square 1, you get 1, and you add 2, you have something congruent to 3 mod 6. When you square 5, you get 1 mod 6, you add 2 to it, you again got 3 mod 6. So again, that means p squared plus 2 is divisible by 3, so it's not a prime number. So from what looked like perhaps quite a daunting, challenging thing to try and prove, when you look at it through the lens of the integers modulo 6, it becomes immediate. It's quite easy once you arrive at the idea of looking at the integers modulo 6. So it seems like a very interesting idea. So we went to the trouble of defining it carefully and establishing some basic properties about it. We're going to continue that today. So very quickly, what we covered last time was we introduced this definition. It's a relation on the integers, a binary relation. So when we're talking modulo n, some fixed number n, if you give me two integers a and b, I give you this statement. A is congruent to b modulo n. Okay? It's a statement. It might be true or false. If we want to assert that it's true, we write it like this: a congruent to b modulo n. If it's not true, we write that as a not congruent to b modulo n. What it means is, the definition we give to it is that the difference between the two numbers, a minus b, is divisible by n. Okay? Or the distance between the numbers along the integer number line, the distance between them is a multiple of n. A couple of different ways you might place it. We very quickly proved a result which linked it to the process of integer division with remainder. A is congruent to b. What that means is, when you divide a by n, you divide b by n, you probably get different quotients. Yeah, if a and b are different, n will go in a different number of times, so you'll get different quotients, but the remainders you get have to be the same if a and b are congruent to one another. So if the remainders that you get when you divide them by n are the same, that means a and b are congruent. So some authors would use that as the definition of congruence. They would say a is congruent to b mod n. What that means is you get the same remainder when you divide by n. And then they might prove a theorem that says, well, that's equivalent to n dividing the difference a minus b. So there may be just two slightly different ways of inventing the definition. Okay. But we want to be able to think about it in all those ways. So sometimes we'll use immediately this version of the definition that n divides the difference a minus b. Other times we might unravel it or use it, translate it as the a and b have the same remainder after you divide them by n. Okay? So we'll be free to make use of either way of talking about it. Then we step back a bit and we introduce some general terminology and machinery, some tools of equivalence relations and partitions. So an equivalence relation is this relation that has very special properties: reflexive property, symmetry property, and transitive property. And this makes it act in a lot of ways like the relation of equality. But it called an equivalence relation, and it produces this strong notion of equivalence amongst the elements. And partnered with that idea of an equivalence relation is the idea of a partition of a set. If you have a large set, there's a very natural operation. You say, well, I don't want to look at all the elements in the large set. I'd rather subdivide them into a collection of subsets in some meaningful way. And I want to do that so that I cover the whole set. Every element is in one of those subsets. And I want to keep the subsets distinct from one another. I don't want to have it ambiguous, whereas this element, well, it's in here and it's also in here. I always want to have these as separate compartments within the big large overall set. And I don't want to have any empty compartments. I want each compartment to mean something. That's called a partition. And it goes hand in hand with the idea of an equivalence relation through this concept of an equivalence class. So when you form an equivalence class of an object X, by definition, that's the set of every Y from the set X, such that X is equivalent to Y. Tilde is an equivalence relation. That's called the equivalence class. And if you have an equivalence relation, the equivalence class is partition your set. They give you a nice splitting of the whole set into these separate compartments in a partition. Equally, if you start off looking at a partition, if someone's helpfully subdivided the set for you in a partition way, then there's a very natural equivalence relation where you say two elements are equivalent if and only if they're in the same compartment, they're in the same subset. That will be an equivalence relation. That was basically where we got to last time. Oh, except and we proved the result, namely that congruence, the relation we're talking about, is an equivalence relation. It is reflexive, it is symmetric, and it is transitive. Okay, so we proved that using the definition. Okay. So any questions at all from last time, or any requests for clarification of any points, or any comments to make about what we did last time? Okay. Okay. So we now have this nice picture. I want to record this on the sheet. So knowing that congruence mod n is an equivalence relation, we now know that it will partition the set of integers. Okay. So we can now view the integer set as being partitioned by the equivalence classes modulo 10. Modulo, sorry, n. For example, so let's do a nice non-trivial example. Okay, so we'll use 10 as our modulus. There's a Venn diagram indicating all the integers, and we can the equivalence classes 1, 2. Okay, just about manage that. We got 10 partition into 10 subsets. Okay, these are the equivalence classes modulo 10. Okay, we don't keep talking about equivalence classes. The name we use is congruence class. So we consider the congruence classes modulo 10. When we're talking about the relation of congruence, we talk about the congruence classes modulo 10. Now, straight away, we can know where some of the integers lie. Okay, the integers 0 through 9, they'll all lie in different congruence classes, and you can start to fill in some of the other members here. 10 will be here, 20 will be here, minus 30 will be here, minus 70 will be here. Okay, you can't complete this picture. There's an infinite number of integers around, but just to fill in some things to show you, 15 is here, 25 is here, minus 45 is here. Everything that's congruent to 5 modulo 10. Okay, everything which is a distance of a multiple of 10 away from 5 along the integer number line, they're all going to be in here with 5 in that same congruence class. You get the idea. A1, minus 9, minus 19. All of those are congruent to 1 modulo 10, etc. So that's our view of the integers modulo 10. Now, we want to fit into this picture. We want to bring, of course, the two key operations on the integers into this picture. Okay. So fundamentally, we can add and multiply the integers, and especially in number theory, we're particularly interested in multiplication, what that means. Straight away, you've got the prime numbers, you've got this idea of factorization, divisibility in the integers. That's the subject of number. But how do the operations of addition and multiplication fit into this picture? Do they mesh well? Do they integrate well with congruence? Okay, it's a bit of a rhetorical question. Of course, they do mesh well. You shouldn't be surprised to know that, because this relation is defined using the concept of divisibility, where two things are congruent modulo 10, if only 10 divides their difference. It's kind of a meshing of divisibility and difference, or a meshing of addition and multiplication. It's not surprising that the operations of addition and multiplication fit quite well. But what exactly do we mean by that? So this is all, what we're going to now is the bunch of results in exercises 4.1. And exercises 4.1 are all around the theme here, is can we extend addition and multiplication, which we know as being operations on individual integers? Can we extend these to the set of congruence classes modulo 10? It's kind of question that's hovering in the background for all of these 6 separate results in exercises 4.1. And they're cumulative, so they're going to build up to the final result. So let's look at the final result, say, in question 6. So question 6 says if f is a polynomial, if f of x is a polynomial with integer coefficients, so f of x, you can think of it as it's some a0 plus a1x plus a2x squared, all the way up to some final term. Okay, it's a function, embodies both the operations of addition and multiplication into it. What question 6 says is that if you've got two, modulo x. Thank you. So m. So you've got two integers that are congruent to one another, modulo sum modulus, any modulus, then f of a is going to be congruent to f of a prime modulo n. Okay? So any polynomial function at all, which we understand as a function of the integers, it's got integer coefficients, so it's going to map integers to integers. Okay? It actually extends automatically to be a well-defined function on the congruence classes, and it fits well on the congruence classes. So if I'm given some polynomial and I want to know what is f evaluated on the congruence class of integers modulo 5, well, in order to actually calculate something, I have to take one of these representatives from the congruence class modulo 5. Okay, I might choose 5 itself, and I might evaluate the polynomial at 5. I'll get some integer answer, and that integer I'll be able to find somewhere in this picture. Let's say it gives me 6, right? Some complicated polynomial, but when I stick in 5, it gives me the value 6. It's 6 there. Well, there's nothing that special about 5. Okay, 5 is the smallest positive number in this equivalence class, but other than that, there's nothing special about it. What if I evaluated the polynomial at 25? Now, if I evaluate the polynomial at 25, of course, I'll get a different answer, probably. Yeah, you put in different arguments into the polynomial, most of the time you get different answers coming out. So if I put in 25, I'll get a different integer coming out. But where will that integer live? It doesn't have the freedom to live anywhere in this picture. It has to belong to the same congruence class that f of 5 belonged to. So if I evaluated this polynomial f at 5 and I got the answer 6, if I evaluated at 25, the value that comes out has to belong to the same congruence class as 6. That's what this question 6 is saying. If you start off with two integers that are congruent to one another, then the values that you get when you evaluate the polynomials, which are probably different integers, but they have to be congruent to one another. Okay? So that's the result we're going to build up to. And we kind of build up to it by doing induction on the structure of the polynomial. The polynomial is a kind of complicated compound object made up out of addition and multiplication and maybe this operation of powers, which is, of course, just multiplication. You kind of think of it as a separate operation, if you like. So the polynomial has been built up using all those methods. So we want to kind of do induction on the structure of that to build up to this final result, question 6. So parts 1 through 5 are just building us up to this. But this will give us this natural idea that a polynomial is a naturally defined function on the set of congruence classes modulo 10. Because if it was the case that, say, when we evaluated f at 5, you got 6, but if you evaluated f at 25, you got 2, well, then we couldn't say that f was a function on the congruence classes, because it isn't well defined. If you chose one representative, you go into one subset. If you chose a different representative from the same congruence class, if it happened that you could end up in a different subset, then the answer that you get would depend on the representative. So it wouldn't be a well-defined function on the set of congruence classes. But question 6, if we can prove it, assures us that it is. So any questions just about the nature of the result that we're going to build up to? Have you got a clear idea of that? It seems perfectly reasonable, okay? Because this relation is defined in terms of divisibility of the difference. So it's a meshing of the two ideas of addition and multiplication. A polynomial is just an addition and multiplication type thing. So it's not surprising that we have this nice view. But we're doing this rigorously in a very pure mathematics way. So we don't just want to take this on faith. It seems reasonable the way I've set it up there, but you know, how do you know it's true? There's an infinite number of polynomials. Some of them get very, very complicated, be very, very long, very large coefficients, high powers. How can you be sure this will always be true? We shouldn't take it on faith. We should build a rigorous, careful argument for it. Okay? So that's what we're going to do. So let's look at the simplest case. So the simplest case talks about addition. So in all the following, we assume, so this holds for all the parts actually. So we assume that A is congruent to A prime modulo n, and B is congruent to B prime modulo n. So if you like in this picture, you know, A and A prime are two things over here, B and B prime are two things belonging to the same set. Okay, so they're different integers, but they belong to the same congruence class, B and B primes. This is quite common when you want to refer to some object and a closely related object. Sometimes we just put a prime superscript mark on the same way. Okay, so A and A prime, B and B prime. So question 1 says, well, if you add A and B, and you add A prime and B prime, if I take A and A prime and add them, if I take A and B and add them, and I take A prime and B prime and add them, okay, I'll probably get different answers. But the point is, I always end up in the same subset. Which one would be? Well, 4 plus 7 is 11, which is 1. So that means you always end up in here. That's what it's saying. If you take something congruent to 4, say, something congruent to 7, minus 3, say, 74 plus minus 3, 71, which is indeed congruent to 1. Okay, so it works out. If you throw a load of examples at it, it works out. But we want to prove it in general. Okay, how do you prove this in general? Well, we use our approach before. Look at the conclusion you're trying to get to. Look at the assumptions you're starting from. Unravel the assumptions. Think carefully about what it is you have to prove in order to get to the conclusion. So this is what we're trying to prove. So really what I have to prove is that m divides the difference A plus B minus A prime plus B prime. If I can reach that conclusion, that's the definition of congruence. This will be congruent to that if I can show that m divides their difference. Yeah. But I know that m divides the difference A minus A prime, and m divides the difference B minus B prime. Yeah, that comes from the assumptions. Well, then I also know that m divides any linear combination of these two things. And the linear combination I'm just going to use is just simply adding them together. Okay, that's one of the very first, well, very second or third properties of divisibility that we proved. That was all the way back in theorem 2.1, part 3. Which said that if m divided two things, it divided any linear combination. Linear combination with integer coefficients. Okay, here I'm just taking a simple linear combination of just adding the two together. And of course, this expression here just reorganizes to that one. Okay, just put the A and B together, and then it'll be minus A prime plus B. Okay, so it's just simple reorganization. So we proved it immediately. It only really took one line. From the assumptions, unravel the assumptions, make use of this result, the divisibility of linear combinations, and straight away we're staring at the conclusion. Yeah. But what led me to do that was because I unraveled the conclusion one step backwards using the definition. And so I had to get m dividing the difference of these two. I looked at what I had. n divides the difference of the a's and the difference of the b's. Well, this is kind of like if I add them together, I'll get this. Yeah. Good, good. Progress. If there's anything you're unclear about, please do stop me and shout at me and ask me. I'll do my best to oblige. Okay, second part, we have to do the same thing for multiplication. AB is congruent to A prime B. Okay, test it out. Does it seem reasonable? Does it seem reasonable? Let's look back at our Venn diagram. Really, I should have put it on the blackboard, I guess. Take two things, say a 2 and a 5. You're going to multiply them. No, let's take ones with representatives. Let's take the 6 and see, I don't have enough other representatives. Yeah, let's give me myself a few other things in there. This is 13 minus 7, 16, 26 minus 4, etc. Let's take two things from here. Say the 6 and the 3. When you multiply the 6 times 3, you get 18, which is where? 8, in this congruence class here. If I take two of the other representatives, take a 16 and a 13 instead. Take a 13 and a 16. Well, 6 by 3 is 8, carry 1, 6 by 1 is 1, 7, and a 0, 1, 3, and an 8, and a 1, 2. 128. Where's 128? It's in that same one we landed in before, okay? And that will always be the case. Whatever pair of representatives you take, one from the 6 congruence class, one from the 3, you multiply them together, you will always end up here. But we want to prove it. We want to show that this has to be the case from the definition. Okay, so in other words, we have to reach the conclusion that m divides the difference AB minus A prime B prime. And we're starting off from the knowledge, from our assumptions, that m divides A minus A prime, and m also divides B minus B prime. Now, the temptation here is just to do something very similar to what we did before. Before, when we were trying to get the additive result, we added together those two things. Now we're trying to get the multiplicative result. So let's try and multiply. Except it kind of doesn't work out so nicely. If you multiply these two, certainly a good intuitionist thing to do. The result you get AB, nice. You get plus A prime, B prime. Maybe not so nice, because we want minus A prime, B prime. And then you also get the, yeah, calm down, Keegan. What you get minus A B prime minus A prime B. Yeah. But that's a bit, we don't really want that. What we want somehow to arrive at is AB minus A prime B prime. So we need a bit of trickery to get there. We need a bit of trickery to get there. You see, this is AB plus A prime B prime. We could write this as minus A into oh God, I'm always twisting myself up with this one. Hang on, it's a bit, I'm getting a bit lost there. Okay, I always get a little bit troubled into this. So I'm going to come at it from this direction. I'm going to attempt to write AB minus A prime B prime. I want to show it's divisible by M. So I'm a bit too, I can't, the stage fright is stop me doing that. So I'll try it this way is slightly safer. I'm going to attempt, thank you, I'm going to attempt to write this as I'm looking for a linear combination. I want a linear combination of things divisible by M. Okay, that's what I want. Because if I can get it as a linear combination of things divisible by M, then I'll know it's divisible by M by appealing to our theorem 2.1 part 3. So the thing to try is to write it as the product of these two things, which I know to be divisible. Both of those are divisible by M. So the product of them is certainly divisible by M. Okay. However, when you multiply those two out, as we saw on the board here, when you multiply those two out, you get this line here. But I want to end up with this. So in order to compensate for that, I'm going to have to add these two quantities on and subtract 2 times that. Yeah? So if I subtract 2 times A prime B prime and add on, what was the other bit? AB prime and A prime B. Everybody agree that equation's finished? So when you multiply those two out, you get this expression here. So how do I make this into this? Well, I have to get rid of these two, so to add on these versions. And I have to turn the plus A prime B prime into minus A prime B prime. So I have to subtract 2. Okay? So that equation is true. But then we look at, I don't want to multiply that out. I want to leave this like this, because I know this part is divisible by M. It's a product of two things divisible by M. And now I look at this and see how I can reorganize this. Well, here, see, I take these minus 2 and I pair one of them with this one and the other one with the other one. And I can write that as a B prime into A minus A prime plus an A prime into B minus B prime. Okay, that was the magic answer I was going for here somewhere. But I twisted around on myself here. Okay. So I've left that alone. And those 3 terms are reorganized into this. Okay. Multiply that, you see it's true. B prime A minus A prime B prime, which is one of these. And here you get A prime B, which is this one, and minus A prime B prime, which is the other one of those. Okay. But if you look at here, this is m divides this, m divides that, m divides that, and m divides that. Okay? So it's a linear combination of numbers divisible by m. Something divisible by m plus something multiplied by something divisible by m plus something multiplied by something divisible by m. Okay? So by theorem 2.1, we get that m divides ab minus a prime b prime. In other words, ab is congruent to a prime b prime modulo. Okay. So that was a little bit trickier than the addition case. The addition is mostly, painfully straightforward. Sometimes the multiplication is a bit of a twist. That's not surprising because prime numbers fall out of the definition of multiplication so quickly that there's something funny about when you extend addition to multiplication, funny things happen. But so there was a right intuitive idea to just multiply together the things we've made assumptions about, and from that will fall out the conclusion about the products, but just a little bit of a roundabout route. And there may be a cleaner way of establishing that, but I've yet to see it. But if you can come up with a cleaner, tidier way of showing that, I think that's good, because that shows you where it comes from. I could have just spat that down on the page and said, oh, when you multiply all that out, you get to this. But like, how did you discover this? How did you come up with that? That's a good question. No, okay. So now we know that multiplication fits very well with the congruence relation. Question 3. Well, question 3 and question 4, these are really just special cases. Really just special cases of 1 and 2, where instead of a separate pair B and B prime, in both cases we use exactly the same integer for B and B prime. Okay? Remember, congruence is an equivalence relation. Everything is congruent to itself. So that's fine. We can C, using C for both B and B prime is fine. C is congruent to C. And so there we just have addition and multiplication where you're just adding on the same thing each time. So questions 3 and 4 go through as well. And question 5 also, that can be proved using induction and part 2. Okay, because question 5 is referring to powers of A. The powers of A will always be congruent to the same power of A prime. But that's just an example of using the multiplicative rule. So if A is congruent to A prime modulo n, by part 2, that implies that A times A will be congruent to A prime times A prime mod n. That's by part 2, where A equals B and A prime equals B prime. It's a special case of part 2, and that is, of course, A squared congruent to A prime squared modulo n. So by one application of part 2, you get 2 squares. If you apply it twice, you get 2 cubes. 3 times you get to power 4, etc. And then use induction. Then use induction to get higher powers. Any questions so far about all those different parts? So although the detail, and especially that multiplicative one, question 2, it kind of becomes a haze of symbols when you're lost. But keep a clear idea of what it is, what it is we're trying to do. We're trying to set out the additions of multiplication and addition. We know them as being defined on the integers. They extend in a very nice, well-behaved way to become operations on the congruence classes themselves. We now know, we're now happy that I can talk about taking this congruence class and adding it to that one. I don't have to worry about which selected representatives I might use to represent them and to do the actual addition operation with. Whichever pair I choose, I know I'll always get the same answer, namely 20, this congruence class over here. Take anything from here, add it to anything from here, you always end up over here. So it makes sense to say this congruence class added to that one is equal to that one. Okay. So the final thing to deal with then is the polynomials themselves. So putting all these together, you deal with polynomial f. Well, let's give notation to all the bits of f. Okay, so there's a general polynomial. It's the sum from I equals 0 to n of alpha I times x to the power of I. That could be any polynomial. Integer coefficients. So the alpha I are integers. Everything's integers. So we're trying to prove this part here that so I'm using alphas for the coefficients because I'm using a's all the time in the question, so I didn't confuse. So I'm switching to using alphas as the coefficients there. I want to show that f of, at a is congruent to f of a prime. And this is where the construction of the thing on the page means more than the final written version, because it's the order in which everything goes down on the page. So we assume a is congruent to a prime, mod n. So I'm going to build a big congruence here in the middle. I'm leaving plenty of space either side. So we start off with the fact that a is congruent to a prime. Modulo m, yeah, agreed. That's the assumption. Space everything out because I want to fit stuff into the gaps. Well, if I raise a to any power and a prime to the same power, it'll still be congruent because that's part 5, yeah? The two things started off being congruent. If you raise them to powers, they still congruent. I'm not specifying what I is. I is just one of the values between 0 and n. If you then choose to multiply both sides by the same thing, multiply both sides by alpha I, the congruence is still preserved. That's an example of part 4. So let's just note down into parts I'm using by in order. So first was the assumption, then was part, well, I did powers first. So part 5, then part 4. Now we've got a bunch of different things labeled I being congruent to their equivalent things labeled I here. But now if I add them all together, I'll do summation over every I and summation over every I here. Again, the congruence is still preserved because I started off with a bunch of things indexed by I. Corresponding things were congruent to one another. So if you add them all up, they're going to be congruent to one another, and that's by repeated applications of part 1. So by part 1 many times, because you got to add up n plus 1 different things. But now what are you looking at? Now you're looking at this thing on the left is simply f of a, isn't it? And this thing on the right is f of a prime. So of course the congruent one. Okay. Starting with the arguments being congruent, the different operations we have to do to build up to the polynomial, each of them preserve this congruence in the middle, which was there at the beginning. Okay. So that's what I mean. When you look at the final version, you know, it's more the story is how dynamically that was built up. Okay. So let's just indicate what we did. So starting with a congruent to a prime, each step to constructing f of a prime is the step that preserves the congruence. 5 parts, 1 to 5 of the question. So not only is addition and multiplication well-defined operations on the congruence classes, modulo n, in fact, any polynomial now, which we understand as a function of the integers, it's got integer coefficients, that extends to be a well-defined function on the set of congruence classes themselves. So that kind of lays the groundwork for some of our future work. Okay? Some of the stuff coming up in the upcoming chapters, we're going to study carefully the behavior of polynomial functions on these modular arithmetic multiplicative groups. I'll use that word group now. We'll be introducing that terminology next lecture. Okay? So when I see you next Monday, we'll do some more work on this chapter, and we'll introduce the modular arithmetic groups, that section that you see at the end of the chapter. Okay, so I'll remind John to just forget, we'll have cryptography tutorials this Friday, and number theory lecture next week, and then number theory tutorials next Friday. Okay?